here. It's EFF Austin, which is dealing with civil liberties in cyberspace, and Austin Science. We should meet Jonathan too. Actually, Jonathan.
Yes, and then professors, and then I also wanted to introduce you to director, senior director at Accenture.
Can you guys go to Dublin? Do they fly you to Dublin? You take me next time. I got cousins.
Only once.
That's why I didn't go to locations, because it was going to be here and then
So, live stream's still on, I don't know why it's gone, and it's still queued up. I messaged you on the Slack, which is always supposed to be I imagine there's 4 or 5 meetups going on tonight. I imagine he's busy. I just didn't realize he didn't push a button. I usually talk for a minute, so I'll probably just go ahead and try to get us moving. We'll get this going as fast as we can. But we obviously have a big crowd. And I only saw one person who was waiting for a live stream, so I unfortunately got to prioritize this.
let me just see, when you're done, I'll just introduce you.
Oh yeah, yes. If you would actually like to do the normal introduction, Luke, he's your friend.
Okay. All right.
We'll cue that off. Sounds good. Let's see. Yeah, if you're going to introduce him, I don't need to pull that up. So.
Hey. All right. So are you still troubleshooting the live stream?
Well, it's just, the issue is it's queued up. It even says ready to start at 6:55, but it's just not ready.
You want to reboot it, or can you?
I can't. It's all Cat Factory.
Okay. Is there anyone upstairs that you know is there?
No. You're going to discover as you work with Cat Factory, there are things you won't like, and too bad because it's free, so you have to deal with it.
So, here's the deal. I did bring a iPad that we could.
Yeah, actually, I would, because yes, Nate is out of town in Houston. He's used my backup recording. So if we want to, actually, if you would like to maybe put the jury rig as something just so we could have some kind of record, that'd be great. Actually, Elijah may get back to me in 1 second. All will be resolved. But yes, let's.
So it's a brand new iPad with a lot of storage.
Yeah.
So do you want to try to live stream it too?
I mean.
Could you log in using this to?
Oh, I mean, could I network to their thing, their account? No, that doesn't.
All right. Just checking.
I know, you're right. And yes, we live stream specifically for accessibility concerns. Not everybody can make a meetup, so we do consider it important, but, we'll see.
Okay, so yeah.
I'll be standing probably roughly over here.
Yes, we can just see.
Maybe get the, if you can get that.
All right. As much as I like me,
No, I think he's the star right now.
reluctantly will agree with you. Okay. Is this kludgy enough for everyone?
You know what?
So,
It's going to give us something. And frankly, probably that will pop in 30 minutes when Elijah sees my message and realizes he hasn't turned it on, but we got to do what we got to do.
so sounds good. Move.
Man, you'd think in a room with this many techniques, somebody would have something.
It's still my house.
Whenever your kludge is ready to kludge.
Just not quite. Just
The angle
literally
is.
at the tipping point.
I mean, can you pull it back, like pull it more this way?
Yeah.
Why don't you turn it around and have it leaning on the other way?
Say again? What do you think?
Back it up.
Yeah, there you go. Man, it's almost like he has a Ph.D. Enough geese, we can screw in a light bulb.
Yeah, how many PhDs does it take to jokes right themselves?
Alrighty. Alright, if you've hit play, then, as I said, I don't...
We want to hit record, actually.
Yes, we do want to record it. Yeah, and that'll probably pop on at some random point whenever he realizes he didn't push the button, so...
Wait a second,
Did he just mess
hung up on
or
something.
something? Is it on?
Hey, come over.
Oh, somebody just told me the live stream is actually working, so I think we're good to go. Let me double check, okay?
So it's saying, what was saying, this would be red if it was red.
Okay, yep, it's live, we're good. Okay, they got it going, we're good. Okay, awesome, okay. Alrighty. Alright, everyone, we're going to get started here. We thought we were having issues with the live stream starting, and we seem to be good. So, welcome those watching home. Hi, John, and welcome to this phenomenal turnout. Welcome, everybody, to the latest monthly installment of the EFF Austin Meetup, co-presented with the latest several times a year installment of the Austin Science Club. So, welcome to all of you. I know many of you, but I also see many new faces. Phenomenal turnout. Welcome all. And thank you for coming and supporting what we do. For those of you who are new or are here from Austin Science Network and are like, who is EFF Austin? Well, I'll tell you. So EFF Austin is an Austin-based, as you might guess, digital civil liberties organization. We're closely affiliated with Electronic Frontier Foundation out of San Francisco. They're the nation's oldest and largest digital civil liberties advocacy group. You can sort of think of them as the ACLU for the internet and emerging technologies. They work to try to safeguard your rights in emerging technological spaces, especially your First and Fourth Amendment rights, free speech, and privacy. And yeah, we've been around almost as long as them. They've been around since like 1990, 34 years at this point. We've been around since like 1991. You're welcome to ask me or our board member John, who was actually there sometime, I don't go back that far, about how Austin was very much involved in the story of the founding of the EFF. EFF Austin is actually the oldest member of what is called the EFA, or the Electronic Frontier Alliance, which is a kind of peer-to-peer activist network of about 100 organizations all around the United States. None of us are formally legally affiliated with each other, but we all tend to believe that technology should serve people and not the other way around. We believe in the rights of ordinary citizens to use technology to empower them, not governments or corporations. So EFF protects and advocates on a lot of vital issues. They mostly work at the federal level. Most EFA groups work kind of at the city or state level. EFF has been involved in such issues as net neutrality, protecting end-to-end encryption, protecting Section 230 of the CDA to let diverse voices speak online, and just, generally fighting the good fight in an increasingly fraught digital landscape. As I said, there's 100 EFA groups around the country, though for a long time, we were actually the only one, not only in Austin, but in all of Texas, actually, though I am happy to announce that as of 3 or 4 months ago, another group here in Austin, Open Austin, is now also in the EFA. They're really cool. You should go support their events as well, especially if you're into civic tech hacktivism, want to learn how to use public APIs to use government data for good. So, mostly what we do is educational. We have meetups second Tuesday of every month at 7 p.m. here at Capitol Factory. We have a usually wide variety of speakers on emerging topics in technology, law, society, even sometimes ranging as far afield as digital art, philosophy, that sort of stuff. And we have, I guess as far as what we have programming coming up for the rest of the year, we were going to be originally here in December, we were going to have a talk from our board member John Lebkowski about trying to explore essentially new paradigms and models of forming community in digital spaces using the old digital community of the well, which has been around since the 80s as a model. Unfortunately, I was just informed the other day that Cat Factory has a space conflict with this room, but that doesn't mean we're not doing anything in December. Stay tuned for, if you check our socials, our Meetup, our Twitter, our Mastodon, our Blue Sky, or our website, and we're even on Facebook, yes. We're probably going to have some kind of holiday party coming up where John will probably give his talk. One of our board members has a performance and community space in not too far south Austin, and so we're very likely to have it there. So stay tuned for that. We'll have a nice little gathering, have a talk, and hopefully whatever other fun things we can come up with. But yeah, we primarily do these talks. If you or somebody you know thinks you might have an engaging talk to give us on some of these topics, we are always looking for interesting speakers. Feel free to get in touch. I know that in addition to John's talk on online community in December, Brianna from Texas Appleseed is going to be talking to us about, I'm not 100% sure, but given her advocacy work, probably the ways in which digital civilities issues impact poor and marginalized communities and how we can try to empower them. Also in February, we're going to have a guy talking about interesting digital art you can make using JavaScript code golfing. So yeah, got a few fun talks coming up. Also, you know, as I said, we've been occasionally known to throw fun parties. If you know eccentric millionaires, please connect me with them. They always make the parties easier. But as I said, probably a holiday party of some kind coming up at the end of the year here. Finally, we do, believe it or not, just like National EFF, we do actually some advocacy at both the city and state level. We were very involved in the debate around automated license plate readers here in Austin. While we regret we were unable to prevent the city from bringing them back, we did get much stronger rules around data retention around them, eventually arguing it all the way down to 7 days, and actually lost by 1 vote, getting it down to 3 minutes. Still biggest regret of my activist career. So we do get involved in these issues. Currently, we've been very much involved in discussions at both the city and state level around emerging AI regulation. We were called as some expert witnesses earlier this year to the State House to speak to Rep. Capriglioni's panel on AI. Gave our thoughts and recommendations about how the state should regulate it. And actually, literally earlier today, we were in talk with one Austin City Council office about our advice on regulating AI. We and Open Austin have been working a lot to talk to various people in the city government about how we think this needs to look going forward. If this all sounds like interesting to you and you want to be involved in discussion, because really we hope to just be a conduit for the community. If you have thoughts and concerns about what our elected officials should be doing on this emerging issue, feel free to get with us. We'd love to incorporate your voice into the community's concerns on how this issue should be handled. All right, I think I've given you most of the upcoming spiel on stuff we are doing. Before I turn it over to my friend Owen here to introduce his friend Luke, who is our speaker this month, talking to us about quantum computers, I also just want to ask, does anybody in the room have any announcements for the community? Shameless self-promotion's totally cool as long as you think it would be relevant and of interest to this community. It could be a conference going on, an event, whatever. Anybody have anything they want to announce before we get going?
Actually, 2 things, and this is more for the Austin Science Network side of things.
Yes, of course, and we thank, once again, we're very happy to co-present this with Austin Science Network. We hope you guys will keep coming back when we have talks of interest to you.
So on Friday, we are going to have a public symposium at the University of Texas at Austin on forever chemicals. Everyone's invited to come. It's at 4 p.m. I have it on the AustinScienceNetwork.com page. If you want to learn from a number of healthcare professionals and scientific researchers, MDs and PhDs and nurses, we'll bring people together to try to understand what's going on. We've got these chemicals in our bodies. We think they're causing cancer, probably delaying puberty in boys. This is no bueno. So that's going to be Friday at 4. Come talk to me afterwards and I can give you more information. It's also at AustinScienceNetwork.com. Again, open to everybody. If you are concerned about longevity, concerned about health, concerned about fertility, concerned about having chemicals that your body does not really know what to do with, that's why they call them forever chemicals. It's open to everybody. And Aaliyah, you want to say something quickly about the upcoming SOMA conference?
Yeah, so this Saturday at the University of Austin, we're having an astronaut summit. This is built around my research where we collect samples from astronauts before, during, and after their mission. So we're having some of our old research subjects back to collect another round of samples. We're also holding a conference around this. So there'll be a day of talks and panels, and there are tickets available online. So let's see, there's not really a word for me to write down the web address on, but it's SOMA, SOMA-summit.com.
Yeah, I should mention this is Elia Overby from the University of Austin, which just opened just blocks from here. So that's exciting. The first kind of astronomy summit we've ever had like this in Austin, I think. Yeah, so y'all should seriously consider joining us for that.
Well, if there are any other announcements, Billy, or otherwise, I will let Owen introduce his friend here.
Yeah, so, super brilliant guy. Take it away, Luke.
All right, that works.
Hey everybody, thanks for coming. My name is Luke Langsjoen. Thank you, Owen and Kevin, for having me. I'm going to be talking today about quantum computing. Before I get started, I wanted to kind of just poll the room. Has anyone here taken a quantum mechanics class? Like say at the college level? A couple? Does anyone have a fairly comfortable understanding of what a qubit is? Okay. Has anybody heard of the word qubit? All right. There we go. We'll start at the beginning, so I'll try not to leave anybody behind. A little background on me before I get started, just to kind of give you some context of where my expertise does and doesn't lie on this, to maybe temper your expectations. So I did a Ph.D. in Virginia. I did my dissertation in theoretical condensed matter physics and studied quantum vacuum fluctuations. And then I went to Madison, Wisconsin for a 3-year postdoc from 2011 to 2014, studying quantum computation for my postdoc. And my postdoc was, as most academic research is very much focused in on a particular nitty-gritty aspect of a very large and broad field, very micro-focused. I was studying sources of noise in semiconductor qubits. In 2014, I left academia. I had a short stint as a securities analyst for a mutual fund, and then since 2016, I've been working for a IP firm here in Austin as a patent agent, writing patents. And I have kept up a little bit on my physics, just in that one of my clients is a quantum computing company, so I've been writing some quantum computing patents. But again, in that case also, it's pretty micro-focused on a very specific aspect of an algorithm or a chip design or that type of thing. So what I wanted to maybe qualify is that I anticipate a lot of questions regarding some interesting articles that were released or papers or various press releases. And I did do some research preparing for this talk, so I know a few things, but there's probably a lot of, it's obviously quantum computing is a pretty big field, and there's probably a lot that I may not know specifically about what this company has released recently and that type of thing, but I'll do my best to answer questions as I can. So a quick outline for what I'll be going over. I'm going to start with a brief discussion of Moore's law and the evolution of transistor technology, so just sort of brief history of classical computing, and then go over what quantum computing is and how it works. So this will be sort of a basic physics description of the basic mechanics of how a quantum computer would operate, and hopefully get everyone up to speed on what qubits are. So hopefully if you all come to another talk, we'll have more hands raised for that question. Then I wanted to discuss what the potential applications are for quantum computing. There's a couple of major ones. And then go over after that what the different physical hardware architectures are that are being pursued to actually instantiate a quantum computer. Finally, I'll have a brief summary of what the current state of the market is for this technology. So, to get started, since before 1960, the capabilities of digital electronic computing devices have pretty consistently grown at an exponential rate, where the number of transistors on a chip have been doubling approximately every 2 years, and this trend has impressively kept pretty steady since the 1970s up for a 5-decade span up to the present day. So back in 1954, we had the Regency TR1 transistor radio, with 4 transistors in it, retailing for $49.95, which adjusted for inflation is roughly $5.85 today. And then if you look at the iPhone 16, from this year it has transistors that are 3 nanometers in length, pretty small, and there's billions of them in your little phone in your pocket, retailing for not much more, about $1,000, with a few more capabilities compared to the transistor radio. So the way that computing power has been able to increase at this impressive rate, of course this is Moore's law, he's the guy that sort of noticed this trend. This trend has continued because the technology has been able to further and further shrink the transistors, and on the silicon chips are primarily used. But there is a limit to this because you cannot shrink a transistor to be smaller than the silicon atoms that the transistor is made out of. the atoms are your Legos that you're building the transistors with, so you can't possibly get smaller than that. And the current iPhone has 3 nanometer chips. If you look at this, you have 10 nanometers is about 20 silicon atoms. These dots are individual silicon atoms from a scanning tunneling microscope. So about half a nanometer is the width of a silicon atom. So we're getting pretty close to the end of the traditional Moore's law progression. We almost won't be able to shrink things anymore here pretty soon. This graph, I gave a talk on quantum computing back when I was doing my postdoc in 2014, which is why this becomes a dotted line here. And I just decided to repurpose the graph. So at the time, there was 13 nanometers was the current state-of-the-art size of the smallest chips that were in production. And impressively, over the last decade, almost exactly a decade, if you go to 2024, it pretty well lines up to where it is now. It's about 3 nanometers. So it's continued pretty well, but pretty soon we'll get to this red line where you can't really continue to miniaturize. And in one sense, that's where quantum computing sort of comes in. It's a little more complicated than that. But you could ask, since our classical computers work so well, why would you need a quantum computer? One way to look at it is that miniaturization is running into diminishing returns. And another kind of maybe a little philosophical way to look at it is that when we're getting to really, really tiny small transistors that are approaching atomic dimensions, quantum mechanics becomes a dominant physical phenomenon at these tiny length scales. And so it's sort of probing the natural next step of where you could go in controlling matter in a computational paradigm. But it's not quite that simple, and I wanted to make an important caveat that there is no chance that quantum computers would ever replace your chip in your personal computer or in your smartphone. There is no plans or anticipation of ever having a general purpose quantum computer. Quantum computers, if they become mainstream and established in the market, they would be for very specialized tasks, a very itemized list. These are 3 examples that we'll describe in more detail later. Prime factorization, simulation of quantum systems, and quantum cryptography. There's other ones also. But the anticipated use cases are not that you would have a quantum chip in your desktop and use that for your PC. That's not what they would be for. They're very, whatever benefits they may have over classical computing would be limited to a very specific set of applications. So, what is quantum computing? Let's start at the beginning. With classical computing, you have bits, which are transistors that can be in one of 2 states, on or off. You map the on to a logical 1 and the off to a logical 0, or vice versa. And you have discrete logic where you have an input. You have a bunch of transistors that can be on or off. You manipulate those in some algorithmic fashion to get an output that is the answer to some problem that you're working on. In the very basic sense, it's not that different from an abacus, really, but a little more complicated. And that's how classical computing works. But it's a deterministic process where you have 1s and 0s that you do operations on to get some result at the end. In contrast, quantum computing uses qubits, which are quantum systems that are prepared in a quantum state, and that state can be in a superposition of multiple modes. And I'll explain what all these terms mean in more detail in a couple slides. A lot of terms in there, don't be scared. But so one example is if you have a spin qubit, which is, say, an electron that can be spinning either up or down, you could have it in a state where it's in a superposition of those 2 orientations, and then you could map the up spin to, say, your logical 1 and your down spin to your logical 0. And in this simplistic sense, a big difference between qubits and normal bits is bits are 1 or 0, whereas qubits can be in a combination of both 1 and 0.
Luke, as a matter of an analogy, does this work for you? So like Linus decided to come tonight, but he could have stayed home. In the classic world, one of these 2 things could have happened, but if this was like the quantum world, he could be a little bit here, a little bit home, and a little bit everywhere in between.
Yeah, do we have to talk about the cat? I have a different analogy that I prefer, but thank you, Owen. Let's have a brief detour for spins. Sorry.
No.
Let me talk about spins a little bit. So classically, we know what spinning is. If you have a ball, it can spin, and the way that you denote spin is you have an arrow that points along the axis that you're spinning, And then the length of the arrow corresponds to how fast it's spinning. So if you could, classically, if you had just a baseball, it could be spinning along any axis, and it could be spinning at practically any speed along any of those axes. So you have a continuous variable, which you define by a vector, which could point in any direction. It's very different in quantum mechanics. In quantum mechanics, a spin, so the electron has a quantity called spin, which is analogous in some sense to classical spin. But instead of it being able to point in any direction when you measure it, it'll only take one of two values for an electron. In general, one of some finite set of values for more complicated particles. But for an electron, it'll always only be spinning up or down when you measure it. But before you measure it, it can be in a combination of those two. And if that doesn't make sense, that's okay. I'll explain it a little bit more as we go. So let's have a little bit of a comparison of some of the differences between classical and quantum spins. With a classical spin, so this you can think of as a baseball that's spinning in a circle, and the axis it's spinning around is that arrow that's pointing off in that direction. You can fully describe how that baseball is spinning with three numbers, the x and y and z coordinate of that vector, if you project it onto the Cartesian axes. You could also describe it in terms of two angles, theta and phi, and the length of the vector, which is usually denoted just by s, the magnitude of the spin. And each of those three, either in the spherical or Cartesian coordinates, those are both continuous variables that can take any of a range of possible values. In contrast, for quantum mechanics, as I was saying, it's quantized to only be up or down when you measure it, and you cannot simultaneously know both what the x and y components are of a quantum particle's spin. You can know what the overall magnitude is and what the component is along some particular direction, say z. And then, as I was saying earlier, in quantum computing, you can then map these two states onto your logical 0 and 1. So if you have three baseballs and you want to describe how they're spinning, you need two n numbers. Sorry, 3 would be 6. If you have n particles, you need two n numbers to describe how it's spinning. This is for the case where we're making an analogy between classical spinning and quantum spin of an electron, in which case the magnitude is always constant, so you don't have to worry about how long the arrow is. So if the arrow is always the same length, then you can define each classical spin just with the two angles. So you need two numbers per spin. And so if you have n spins, you need two n numbers. So for 3 particles, you need 6. In contrast, if you have a quantum state of 3 spin 1/2 particles, you need 2 to the n, 2 raised to the nth power numbers to totally specify an arbitrary state of those 3 particles. And the reason is that you have these 2 to the n numbers, which for 3 particles is 8, 2 to the 3rd is 8, and that's these 8 coefficients, a. And what these different terms are is they're each different combination of spin up and spin down for each of the 3 particles. And so the general state for having 3 quantum spins is all combinations of spin up and spin down for the 3 particles. And the point is that the amount of information that can be encoded in principle in these 3 classical spins scales as the number of particles, twice the number of particles. In contrast, for a combination of quantum particles, the amount of information you can encode in this combined state scales exponentially with the number of particles. And this is sort of a hint at a first way of understanding how quantum computing is able to have increased computational power over classical computers. Yes?
Can you circle on the lower equation the 3 different spinning dudes?
Yeah, sorry, yeah, thank you. Let me clarify the notation here. So this is the overall state of a set of 3 spin 1/2 particles. These A's are coefficients, just numbers. And then these 3 are ket vectors, which represent the quantum state of 3 separate electrons.
So 001 is spinning 1, spinning 2, spinning 3.
Yeah.
Thank you.
Yeah, so in this one, 2 of the electrons are spinning down. If we say down corresponds to 0, and then 1 of them is spinning up. And so this is all the combinations of different electrons being up or down, right? So you have 8 different combinations of up and down. So qubits are able to encode more information, especially as you scale more of them, because they have this combinatorics of the combinations of different states for each particle. So if we go up to 4, then you can see this becomes 8, and then 2 to the 4th is 16, so you get an even bigger difference between the 2. Yep.
Do they influence each other to make these combinations?
Do they what?
Does one qubit influence another qubit to force this number of combinations, or it's just simple math?
No, so there are interactions, there can be, between qubits, but this is prior to considering anything about interactions between them. It's these are just the number of combinations of states if you have...
Yeah, simple
right,
math.
Simple math, exactly.
Thanks.
Yes, Kevin.
I may lose half the room with this, but trying to remember my own memories of this. And this is ultimately a consequence of that they are fermions, so that they don't the spin quantum vector. It's unique essentially. They don't degenerate essentially.
That's not that's not directly related to this,
Okay, I wasn't
this
sure.
factor. No, because this could be true even if they're separate from each other.
Okay,
Right?
okay.
It's not so that they're all on top of each other.
Okay, cool.
Any other questions so far? Okay, well, we'll try to get you guys up to speed. So, all right, so backing up a bit. So if you have this complicated state for your four spins, it's in some combination of all combination of states, but then if you measure the spins, the wave function will collapse onto one of these, and the probability of it collapsing onto any one of these is related to these coefficients. These coefficients are actually the square root of the probability. Probability amplitudes. But at the end of the day, when you measure spins, they do give you just, each one will be up or down. But that's not until you look at it and shine light on it or whatever you do to it in order to determine which way it's spinning. So I'm gonna stop talking about spin, because spin is confusing. What does it mean for a particle to be spinning both ways at the same time? And this is another metaphor for understanding quantum particles that I think is a lot more intuitive. So forget what I was saying about spin for now, and think about a drum head. So you have just a physical drum head, and you strike it gently in the middle, it'll vibrate up and down, and it'll vibrate in a way that looks like this. Maybe this is a little exaggerated in terms of the amplitude, but it'll vibrate up and down. If you strike the drum head with a higher frequency or at different locations on the drum head, you can excite higher excitatory modes of that vibration, higher harmonics, standing waves of the drum. And this is also true for other types of instruments, brass instruments, and even like Hungarian, dual tone singing. You can have a note that has both a primary tone and also higher harmonics that all exist at the same time in a single note that you hear. And a single tone, if you can find them on the internet if you just want to listen to what just a 44 hertz, or is that an audible range? But if you want 440 hertz, if you want to just hear a single tone, it doesn't sound very well. It sounds kind of caustic. But most more pleasant sounds actually have a lot of higher harmonics that are present in the spectral distribution of the sound, so that when you hear a nice singing voice, it'll have higher tones aside from the bass root note that the singer is vocalizing. So I think this is a little bit more of an intuitive way to conceptualize what qubits are doing and how they can be in multiple states at the same time. So a qubit, a wave function, is a wave, and one difference is that this wave is a physical membrane that's moving, whereas the wave function is a probability amplitude which doesn't have a direct physical analog, so this is a metaphor of sorts, but it still, I think, helps to visualize it. So when we say that when a qubit is in a superposition of different states, think about it as it's a wave that has multiple modes that are vibrating at the same time, typically with different frequencies. And the overall behavior of the qubit is the adding up of those different vibratory modes to get an overall behavior similar to a more pleasant singing voice that has overtones. This is relevant for quantum computing because this can help to understand how quantum computing is effectively able to accomplish massive parallel processing. So if you think of each of these different modes as being your ones and zeros in your computer, and you have a single qubit that's in multiple states at the same time, and you're doing an algorithm on these qubits, on the ones and zeros, to get out some answer. So you're processing the ones and zeros and doing things to them in combination with a bunch of other qubits to end up at some result. Each qubit is able to do multiple things at the same time because each of the different modes that it has in its wave function will react differently to whatever interactions or perturbations you put onto it. And by carefully controlling what those interactions are and carefully designing your algorithm, you can make it where each of these different modes that are contributing to the wave function of the qubit are able to contribute separately to the to arriving at the answer to your computation.
Wow. Sounds good.
Great.
Everybody got it?
This is the key point, so I'm going to pause for a second if anyone has any questions on that. Yeah.
So here we do have this wave function of one qubit somehow working with other wave functions of other qubits, and you can combine different parts of those things to come up with another wave function which might be 0, 1 or something.
Sure. Yeah. So yeah, that's a great question. The one fascinating and kind of confusing thing about quantum mechanics is that when you have multiple particles, it's really just like adding more modes to an overall system, because once you have 4 particles, that just becomes one larger wave function that includes all 4 of them. And so the number of combinations of different modes for each of those particles then scales exponentially. And so it's having 2 qubits that are coupled together in some environment is, you can look at it as 2 qubits, they each have their own states. It's also, you could look at it as a larger 2-particle wave function that includes both of those. And so this same logic of having multiple modes that exist simultaneously applies both to the different states of a single particle and to the different particles that have their own states. Those all sort of, at least in the hand-wavy metaphor, contribute to these different
So
modes.
in all this, do you always go for 0, 1, or can you go for more?
No, you can go for more. There's lots of research into algorithms that use, they're called qubits for d-dimensional.
Oh.
So 0, 1, 2, 3 would be I think that's a tri-bit.
A trip?
A tetrabit.
Tribit? Tribit, maybe?
0, 1, 2, 3, tetrabit.
Tetrabit? Yeah. Yeah, but yes, they have, there's algorithms that look into, rather than just having 0 and 1. And typically 0 and 1 is used most common.
Is it similar to the reasons that even though we could use trinary in classical computers, we don't, because it's just simpler?
That's a great reason. Sorry, I don't know what happened. I was babbling too much. Another reason also is that when you have only 2 states, then typically it's really tractable how to transition between those 2. And once you have multiple states, let's say an electron and an atom has lots of different orbitals that it can be in, which would be different states. But in a computer, if you want to very controllably move the electron between those different orbital levels, you need to have different frequencies of lasers. And if you're trying to just get some computation out, you typically want to be able to controllably just move it to exactly where you want back and forth. So there's other complications.
I've got tech support to get your screen back.
Great, thank you.
Unplug and replug.
That's probably going to be all it is.
Usually that's the solution.
And this outlet's on, right? So I'm not running out of battery.
How many PhDs does it take to change a qubit?
Just unplug the.
I don't know
display.
actually.
Great.
Do you think it may have died?
Actually, it's turning back on.
I can plug it down here for the charger.
Yeah,
Try
let's
that.
try a different outlet.
Alright, it seems to be working.
Oh, it's working.
Great, okay, yep.
There we go.
Yeah, let's try the wall.
Alrighty.
Okay, sorry for the delay, you guys. Let's
Thank you,
continue.
Elijah. Elijah, everyone.
Thank you, Elijah. So this is the end of my basic introduction to quantum computing talk. Sorry, in terms of the physics. So any other questions before we move on to? Yes, sir.
So in order to read the answer, it's going to be a probabilistic read, like a little one of those states.
Mhm.
So is the goal of the algorithm to like read one of those 8 coefficients really, really big?
Exactly. I'll discuss that later, but that's exactly right. So some of the potential benefits of quantum computing are, as I was saying, this massive parallelism, as each qubit can simultaneously exist in a superposition of multiple states, and that the number of states gets exponentially larger as you have more combined qubits. And so these different states can undergo computational manipulation. For each of these states simultaneously can undergo their own manipulation in order to increase the informational bandwidth that you have to do some type of algorithm or computation. A second, somewhat related but kind of distinct advantage is that quantum systems have advantages for quantum simulation because they are quantum systems. So there's a big field of quantum computing is using a controlled, and I'll talk about this more later, but using a controlled set of qubits to emulate some physical system of interest, and then tweaking the parameters of your control in order to probe different physical properties. But I'll get into that more a little bit later. So this all sounds great. Why don't they exist everywhere? What's the problem with them? There's a lot of difficulties. Qubits are what we scientists like to call very, very small, typically, and they're very delicate, and they have to be very carefully prepared and isolated from the environment. The reason that we don't see Zoltan both here and at home and walking between is because he's much larger than most quantum particles are. And anytime you get to this length scales of our normal experience, all of the thermal noise and other chaotic microscopic motion in the environment will destroy any coherent relationship between the different modes of a quantum particle. So you only see quantum behaviors typically at very, very small length scales or at very, very cold temperatures. There's a few exceptions to that. Geckos are an interesting one. They actually use the Casimir effect attached to glass, but there's not very many cases where quantum mechanics is observable in our everyday life.
Schrodinger's cat conditions apply. It's got to be a very small cat.
Exactly. Need a very, very tiny cat. Yeah, so room temperature environments have enormous amounts of thermal noise from the perspective of your typical qubit, which leads to what's called decoherence. Decoherence just means you mess up your qubit. It starts off in some controlled combination of 1 and 0, and noise from the environment will just bombard it with chaos, and you have no idea what it's in anymore. So the thing about quantum computing is that not only does the qubit have to be in some combination of 1 and 0, you have to both know what it's in and be able to control that in order to do some useful computations with it. And if you have, you can just, if you've seen like the videos from a microscope of Brownian motion, if you look at particles on small scales, everything's just moving around chaotically all the time and just destroys everything in terms of quantum coherence. So maintaining a stable qubit environment is very difficult and expensive. Another really important point is this control isolation dilemma. So you want to make a qubit in some known state, and you want it to stay that way and not get messed with by your environment, but you also have to interact with that qubit in order to do a computation. You have to be able to switch it back and forth you have to be able to have it interact with other qubits. And the tools that you use to interact with it are not controlled, isolated quantum systems. Typically, they might be some little metal device that you use to apply an electric field, and that has its own source of noise. So there's sort of a bootstrapping issue where you ultimately have to use something that you don't have quantum control over in order to make this isolated, perfect quantum system. And the tool that you're using to do your computation can also be a source of noise to disrupt that quantum system. And so there's sort of a trade-off there that's difficult.
Question?
Yeah.
Is it always obvious whether you have coherence or decoherence, or did you not know?
That depends on there's some architectures where it's pretty easy to tell, and I'll have a few slides later that kind of show it. But it's certainly if you're designing a quantum architecture, you want to make sure you can tell, because otherwise you have no idea if your answer is right or not. And actually, some of the early, like maybe 5 or 6 years ago, some of the early announcements from IBM and some of the other big researchers where they said they had some 20 qubit computer, a lot of the pushback from the physics community for some of these early devices was, well, yeah, you haven't proved that that you even have quantum coherence. You just you put some stuff in a box and spit out an answer and said it was, a quantum result. So that's a very relevant question. That's certainly a big part of the research. Yeah.
What is coherence? I mean, quantum, in chemistry, it's like the electron jumps up and down in certain sets.
Right.
Quantum. But what is decoherence when it comes to one bit, and what is quantum about that?
Sure. Yeah. Great question. So remember when I had the example wave function of the qubit that was a coefficient a times up plus the coefficient b times down? So for the purposes of this talk, you can understand coherence as meaning that you both know what a and b are, and you can control what they are. And if A and B, say that's an electron, if that gets bombarded with thermal noise, then suddenly it's still in some superposition of A and B, potentially, but you no longer know what those are, and it's not the A and B that they're supposed to be in. And that's then
So
decoherence.
coherence means I can understand it
It means that you can control it.
or control it.
So you prepare, so initially the way quantum computation works is you prepare a quantum system into some known initial state, then you do a sequence of steps and gates on it to influence that state. And if it's ever not in the state that it's supposed to be, or then you don't know what the state is, then that would be decoherence.
Thank you.
Yeah.
Would a classical analogy be like you've got your SSD and a cosmic ray hits it and flips a bit to a different value, and now I don't know what's in there anymore?
Sure, yeah. It's a great analogy. So that's the first page of difficulties of quantum computing. Here's another one. Quantum error correction is a lot more difficult than classical error correction. The next slide will get into that in more details. Also, this relates to, I believe, your question, I believe. So even without decoherence, quantum operations are inherently probabilistic, whereas classical computers use deterministic discrete logic. So in a classical computer, if there's no bit flips, you go through an algorithm, it'll spit out, your calculator will give you the same answer to anything you put into it every time, right? That's different from quantum computers. One example case is a simplistic case, but say you have a binary question that you wanted to ask your quantum computer. One way you might do that is you have your initial state where it's in an equal superposition of 0 and 1. You do a bunch of steps to it to get what the answer is, and the answer, so 0 and 1 are your two potential answers. At the end of the day, you end up in this state and you measure it, and you're much more likely to get a 1 when you measure it than a 0. The probability is the square of these two numbers. And so if you get the 1, then you assume that's the answer, but there is still, even if everything works perfectly, there's a chance that you could get the wrong answer, assuming 1 is the right answer here. And the way that this is addressed is you typically would most algorithms, you can run them longer to increase the discrepancy between the two answers, to increase the likelihood of getting the right answer. So if you do a short algorithm, you would get, say, 0.75 here, but the longer you run it, you can increase the probability that when you measure it, you'll get the right answer at the end. But it's still fundamentally probabilistic whether your answer is correct or not, and there's no way to get, even with no errors, there's no way to get a 100% chance of getting the right answer. But you can get, asymptotically as close as you would like. So
these, my functions are, in discrete, but these are probabilistic, so are they idempotent? In other words, you just run the damn thing over and over, or it's a wave state that you hold for a longer period of time?
The former. You'd run a series of gates on it iteratively to further distill the answer. You can sort of look at it that way. So one more slide on quantum error correction, just to kind of give you a flavor for what some of the difficulties are with this. In classical error correction, typically it's addressed by using redundancy, whereas instead of using a single bit 0, you would have 3 copies of 0. And if you receive a 001, you would assume that it's more likely that that 1 got flipped than both of the zeros got flipped, so you'll change that to 3 zeros again. And so redundancy can help reduce, if there's a single cosmic ray that flips one of your transistors, then you can determine that that this was actually still a 0 even with 1 bit flipped. You do an analogous thing in quantum error correction where you encode, instead of A0, B1, you have A with 3 qubits, 3 electrons potentially that are all in 0, plus B with 3 electrons all in 1 as your encoded state to give you redundancy. But there's at least two difficulties with this. One is that for classical computation, you only have to worry about bit flips. So 0 goes to a 1, whereas in quantum computation, you can both have 0 going to a 1, or you can have 0 going to -0, which is called a phase error. More generally, you can have any phase between these two that will mess up your calculation. I think an even bigger problem is that in classical error correction, say you receive a 001 set of bits, and you're like, oh, flag that as an error, let's fix that and turn it into all zeros. For quantum computing, you can't just look at the state that you receive and see if it's 001, because that would involve measuring the qubits, and that would destroy your quantum information, and you wouldn't be able to continue the computation. So in order to identify when an error occurs in your redundant state, you have to have these sort of indirect methods of measuring something that's indicative of an error probably having had occurred, and then sort of deduce what's the more likely case of what error did occur to probabilistically, hopefully fix the error that occurred. Because you can't just look at it and see what it is, or that will mess up your quantum coherence by measuring it. Right? So if you measure this, if this is your overall state, and say one of these was a 1, and you measure it to see if that's the case, then it collapses this into just one of those states, and you no longer have the coherence between your two modes. Yep.
Seems like a lot of extra work.
It is a lot of extra work.
And it's still, obviously it's still faster in some situations.
No, it's never
Because
faster.
You can,
Not currently.
okay.
Maybe it will be one day.
Cool.
This slide gets
That's what I was
to it. Yeah,
It seems.
we're catching up.
Okay, all right.
So,
Time for another.
yes, sir.
You said introduced the concept of phase error, and I'm not sure if I missed something. That earlier slide about the capital A vector, or I don't remember you introducing the concept of phase.
I did not. I'm sorry, I glossed over that. So yes, so these wave functions are typically described as these coefficients A and B are complex values. So a complex number you would describe in the complex plane. That's why I glossed over this, because maybe we'll in the weeds. But the complex plane is, you have your real axis and your imaginary axis, and so you have an angle, which is where you're pointed along that axis, the relative strengths of your real and imaginary components. The phase is that angle in the complex plane. And the phase error means that you have an error in that. So rather than an error in the magnitude of B, it's an error in the relative strengths of its real and real and imaginary components.
Is it correct to say that it flipped to its complex conjugate, or is that not quite it?
It could just perturb it a little bit.
Oh, okay, it could perturb in any way.
So
Okay.
positive to negative is a 180-degree flip.
Okay, gotcha.
But it could be any,
Understood.
right, any angle.
Luke,
Yep.
I think Daniel Mahler told me something like he thought maybe a 400 physical qubit quantum computer would have the error correction
It's scalable in order
to be really more generally useful.
right. No,
Okay.
I have some slides on that
Okay.
also. We'll get to it. Sorry, you guys are jumping the gun. All right, so at a high level, right, it's actually, here we go. Next slide. To build a quantum computer, you need to be able to do all these things without disturbing your states unintentionally. In other words, you have to control the quantum evolution of the state without destroying quantum coherence. And a figure of merit that's good to keep in mind is the ratio of the coherence time, which is how long your qubits will stay in the state you put them in before they're in some random state from being perturbed by the environment that you don't know and can't control. The ratio of that to the gate operation time, which is how long it takes to do an operation on your qubits. And in general, rule of thumb is you need a figure of merit greater than 10,000 for a scalable quantum computer. So not 10 to the fourth, not 400, but yeah. Probably
Kind of a big difference.
There's a 4 and a 10 in there. And the reason that this is 10,000 is because you need to have extra room for quantum error correction and all these other things that complicate your ability to do useful computations with a qubit. So you want fast operations and long coherence times in order to have a functional quantum computer. So will there be quantum supremacy? Quantum supremacy means that there's a particular problem that can be performed better by an existing quantum computer than any classical computer that exists. That's so strictly better, right? If a quantum computer can decrypt public key cryptography that no classical computers can do in shorter than 1 million years, that would be quantum supremacy. And the answer is not yet, but maybe. So the question is whether the overhead from quantum error correction, maintaining coherence at larger scales as you scale the computer up with more and more qubits, the physical constraints on gate speeds, etc. Can all of these issues overcome the scaling advantages of the parallel processing that you get by quantum computing? And that's currently an open question. There are some prominent physicists that still recently published papers arguing that it's categorically impossible for this to ever happen, that the difficulties involved in making these things work they just overwhelm the potential advantages that you might have. On the other hand, there's billions of dollars of investment that's currently going into trying to solve this problem, and they've made a lot of progress in the last couple of decades, so we'll see. I think it's an open question. I will say, when I was doing my postdoc 10 years ago, I was pretty strongly in the red camp back then. I was pretty cynical about it. I was like, yeah, it's not gonna work. Since then, I've become a little more open-minded. I'm not really convinced one way or the other, but I think I've been impressed by how much progress has been made in it, and there's a lot of impressive physics.
Do you currently have a ballpark of what you would say? So you think it's possible maybe to go to quantum supremacy? Do you still have kind of maybe an upper limit of you don't see us ever getting more qubits than X, that it won't scale beyond that point?
I don't have that in my crystal ball, no.
Okay.
Yes, sir.
Is the amount of dollar investment increasing year?
I have a slide on that later. You guys have great questions. I didn't anticipate them. I thought this headline was funny. This is a Nature article from last year. Quantum computers, what are they good for? For now, absolutely nothing. But researchers and firms are optimistic about the applications, and that's really where we're at currently. And I think it's very much still an open question in the community whether these will work or not. Okay, so what could quantum computers be good for? Here's three major examples. There's more, but really the first one was Richard Feynman in 1982 postulated quantum simulation, just the idea that if you have a simpler controlled quantum system that could be used to simulate the behavior of some more complicated system that you're trying to probe the behavior of. And there's a lot of applications of this type of thing. There's also Shor's factoring algorithm by Peter Shor, this handsome devil. And this solves the prime factorization problem in polynomial time, which I'll explain more in a bit. And then Grover's database search algorithm increases the scaling of how long it takes to search a database for some desired entry, instead of scaling with the length of the database to scale with the square root of the length of the database. So pretty significant.
And that's
speed
an
up.
unsorted database, to be clear, yeah?
Yes,
Right.
I believe so.
Well, because I was thinking you could do binary search if it was sorted, so, yeah.
Right. So for the first one of those, quantum simulation. What does this mean? So that you construct qubits in a controlled quantum system that map onto a physical quantum system of interest. And then different physical materials can be simulated by simply modifying parameters of the qubit interactions, for example, the amplitude and frequency with which you interact with the qubits. That can be used to probe different physical materials. And this has a lot of potential use cases for emulating complex materials that can help discover and design better semiconductors, insulators, and superconductors. So a bit of just background on, say, superconductor research. They're really useful and fascinating materials that have zero electrical resistance and are useful in lots of applications. And there's a lot of research effort into discovering different types of materials that become superconducting at easier temperatures and pressures, and they're easier to make, cheaper to make. And the way that research goes typically is you're trying lots of different combinations of chemical arrangements with different doping and different crystal structures to see, okay, if we have this particular weird, combination of a bunch of different elements in this particular arrangement with these layers, what will its electrical properties be? And that's a very active field of research, but one of the difficulties is that to tweak your model a little bit, you have to remake a whole new material, which can be pretty expensive. The idea with quantum simulation is that you could have your controlled qubit environment, and by simply tweaking a knob that changes some of the parameters of how your algorithm runs, you could probe different types of materials much more easily. And then there's also a lot of applications for this in pharmaceutical development, protein folding, and that type of thing, just to try to model and understand complex quantum systems. Just to give an update on where this is at currently, this was a paper that came out of MIT this year. Rosen et al. Are the authors. This is a 16 superconducting qubit quantum computer. So each of these little crosses is a superconducting qubit. I'll explain more what superconducting quantum computers are later. But what this paper showed was that they were able to generate synthetic electromagnetic fields on this computer. Pretty cool. What that means is, so you have these 16 superconducting qubits that are each in a state. They have nearest neighbor interactions where they interact with each other. And by fine-tuning the energy levels of these qubits and their interactions with each other, they were able to simulate the behavior of electrons in a real magnetic field, where there is no magnetic field active here. They have qubits, but they were able to map those two different physical things onto each other. On one hand, you have your computer with these qubits in this controlled state. You're carefully controlling their energies and their interactions. And then they're able to map that onto how electrons would behave in a real magnetic field and controllably adjust what that magnetic field strength is. So a pretty impressive just first step towards quantum simulation that they were able to do this. I thought this was a really neat paper. But you know, we already know how electrons behave in magnetic fields, right? So this isn't, we didn't learn new physics from this necessarily, right? To bridge the gap between this paper and a quantum supremacist, is that how you say it? A really good quantum computer would need to be able to emulate how a protein folds that you have no idea how that would work with your normal ways of calculating what it does, right? So this is, but it's a proof of concept and step in the right direction. They were able to emulate how electrons behave in magnetic fields using superconducting qubits. They use what are called transmon qubits. Transmission line shunted plasma oscillation qubits. What a name. Another potential use case is prime factorization. So if you have a subprime number is a number that is a product of two prime numbers. So 15 is subprime because its factors are 3 and 5, besides, of course, itself and 1. Those are obvious. That's pretty easy to solve, but if you get a larger subprime number and want to figure out its two prime factors, that gets more difficult. So these two numbers multiplied, these are both prime, and they multiply to give you this 56 million and change number. And for all classical algorithms that we know of to solve this problem, the amount of time that it takes to find your two prime factors scales exponentially with the length of your subprime number. And this is used in public key cryptography. They typically use 2048 or 4096-bit keys. And the way it works, in a very oversimplified hand-wavy sense, is this number would be your public key that you share. Your private key that you know would be one of these two prime numbers. And imagine that these are both 100 digits long, so it's a much harder problem. Like a computer could figure this out for too long. But it's really long, so the computer can't figure it out. You have one of the prime numbers, you receive the public key, you're able to divide those two to get this other number, which is the security key, which you use then to authenticate to log into whatever the security purpose is. This is the magic number that you get. So the point is that it's safe to share this publicly because you can't do anything with it unless you know what this is, and it's too difficult to factor this to determine what those two are from scratch with brute force. Anyway, so one of the potential use cases for quantum computation is that there's algorithms, Shor's algorithm, that shows that you can solve this problem in a polynomial time, meaning the amount of time it takes to solve it scales as a polynomial of the length of your subprime number rather than exponentially, so that potentially a quantum computer could break all public key cryptography. So recent developments, where is this at currently? There's a paper this year. Chinese researchers at Shanghai University used the D-Wave Advantage computer to decrypt a 22-bit RSA key. Which 22 bits, 2 to the 22, is a 7-digit number. So you have 7-digit prime number, and they were able to decrypt that. Currently, we have 2048 and 4096-bit keys are most widely used. So what they did is a long shot still from disrupting public key cryptography, but again, they're making progress towards it, right? So these are 600 or 1200 digits long. Here's what's currently being used.
You make it sound like it's a good thing that they're doing this, Luke.
I'm value neutral on it. But this change is going to happen. We'll see what happens.
Do you actually believe the Chinese did it, or they're just lying about it?
I don't know.
Okay, never mind. So what about this? Is this the Bitcoin crack the Bitcoin problem or not?
No, this is different. Although they're probably related.
At least I couldn't speak to the physics, but to the practical standpoint, like, do you like online banking? It's not safe to do if they figure this out.
Sure, right. No, I'm not.
No, Bitcoin, no.
Yeah, I'm making no value judgments on how good this would be for society, but this is where it's at currently. And just for context, the D-Wave Advantage is a hybrid quantum classical computer, which is one of the more popular methods where it's not strictly a quantum processor. It has both quantum and classical components that outsource different parts of the computation to both of those two to sort of optimize the strengths of both types. It uses what's called quantum annealing, which is kind of a neat method. Basically, you have qubits that are in a state, and you gradually modify the energy environment of this state to move it into a different state, and you structure it in such a way that the final state it ends up in corresponds in some way to the answer that you're looking for, so that you're able to then measure it in that and to get your answer out. And quantum annealing is optimized for solving combinatorial optimization problems. This was actually not done with Shor's algorithm. It was done with a different algorithm. Yep.
So in your simple example on the last slide where you're trying to find the prime factors of 15, would the answer that you're getting out of the system be, let's say you had 3 qubits, basically be an example where the probability on the qubit that would have the binary representation of 3 or 5 would be the right answer, and you're reading that as being the highest probability?
Yeah, that's a good way to think about it. Yeah, so your measurement would come out with something that, that maps to the number 3.
And so how do you build this system? Maybe it's beyond the scope of the talk, but are you using gates that are similar to like the ALU gates on a classical CPU? They're built out of quantum?
The answer to that is there's several different ways, which I will get to on some slides. Yeah, there's a number of different ways that this can be implemented. A third use, which is related to what we just went over, is quantum cryptography. So yeah, quantum computing has the potential to make all encryption methods obsolete, which would make online banking difficult. And I will give you that. The other side of this is that it does also have the potential to introduce new and more secure encryption methods. Excuse me. In particular, a quantum encrypted message could use entangled quantum states. Basically, you have your 2 particles that are in 2 states. They're in an entangled state where it's a combination of one large wave function. You send one of those 2 particles in a message and keep the other one back to send it to some recipient. If a third party intercepts it and then tries to look at it to see what that is, it will destroy the coherence between the states, and so you can have messages that are not eavesdroppable. Because if someone tries to intercept and look at the message, it will destroy the coherence between the 2 states and render the key useless. So there's some interesting ideas about having secure communications using this. This is obviously another whole big bag of worms to figure out how to make that work, but this, if we have quantum supremacy at some point, then this might be what would replace our current public key cryptography. Yep.
I find myself wondering if the security is given by that anybody who tries to look at it will collapse it and there'll be nothing to look at. Couldn't they use the very techniques of quantum computer coherence and operating on it without looking at it to try to decrypt it, or is that actually impossible for other reasons?
Yeah, it's impossible for other reasons. I mean, you can still make it where, so you would typically do this with a couple back and forths also.
Okay, a handshake.
Right, handshake type of thing,
Yeah.
right? And then, then if they tried to intercept it to do anything with it, then it wouldn't work, so,
Okay.
right? So, then I guess, the hostile third party could still intercept messages just to destroy them, and then you can't talk. but they couldn't learn anything.
Some kind of a quantum DDoS, no talking for you.
Right.
I was just going to mention something. So if any of y'all like passwords, any of you like encryption, especially about healthcare data, which more than a few of us in this room have been dealing with, for what it's worth, I talked to the director of the National Science Foundation about a year ago about this stuff. I just asked him, when is quantum computing going to affect cybersecurity? And things like protecting passwords and encryption. He said this decade. So he's not talking about 30 years in the future. He thought this decade this stuff could break our current encryption regime. That's why the idea of the Chinese government having this just terrifies me. But anyway, sure going. You didn't need enough. If you didn't have enough to worry about this.
Another interesting application is quantum machine learning, which I'm not an expert on, but I just did a little brief research on this. This is just integrating quantum algorithms with machine learning. There's a couple algorithms that are anticipated to be useful. Hero-Hasidim-Lloyd, the HHL algorithm, numerically solves systems of linear equations. Those are used for training machine learning weights. And also Grover's search algorithm is supposed to be useful. Potentially machine learning models can be trained more efficiently with an effective quantum computer.
Which might reduce their energy requirements,
Yes,
which we
exactly.
hear a bit about.
Although quantum computers are not typically sold on their energy efficiency.
No, it takes a bit of energy to hold that coherence.
You got to keep it down at 3 Kelvin for a long time.
For those of y'all who don't know the term machine learning, we're talking about AI. Just
Right,
That's it.
yeah. All right, physical implementations for quantum computing. How do you actually build these things? Which gets to with your question about how do you actually would do this. There's a bunch of different, this is a short list, there's plenty more beyond this. I'm gonna talk about these top 4 a little bit in a little bit more detail. First is solid state quantum computers. This is what my postdoc research was related to. I was studying, these are metal gates, you have a quantum dot where you have an electron that's confined to exist within one of these 2 circles, and you apply electric and or magnetic fields to these gates in order to confine the electron and manipulate it and move it back and forth. My research was studying evanescent wave Johnson noise, which is a type of noise that comes off of metal surfaces in their near vicinity. So I was just, as I was saying, it's very, very micro focus. I spent 3 years just looking at how that noise behaves next to a piece of metal, was what I was studying. But the larger, more broader context is that you have these silicon germanium heterostructures. You typically confine the electrons to this red layer of silicon, which is sandwiched between 2 silicon germanium layers. They then have metal gates on top that are used to confine and control the electrons. There's 2 types of qubits that are typically used in this setup. You can have charge qubits, which are where the 1 and the 0 corresponds to an electron moving back and forth between these 2 spots. So it on the left would be a 1, it on the right would be a 0. And it's called a charge qubit because you move it back and forth by applying an electric field, which interacts with the charge of the electron to move it back and forth. A second type of qubit you could have is a spin qubit, where you manipulate it with magnetic fields, and the 1 would be spin up and the 0 would be spin down. So you flip it back and forth in order to do computations. And one advantage of this setup is that it's relatively easy to measure. You just need to measure the current through the quantum point contact, which is this little channel here. And the current that you get for a given voltage will vary very strongly on where the electron is, for obvious reasons, and also based on what spin it's having. So it's fairly easy to tell what the state is of the qubit by just measuring this current. And for scale here, this is 200 nanometers. So some advantages of this setup are that you can repurpose existing semiconductor silicon chip fabrication foundries. There's obviously a very well-developed field. You need some changes to it, but you could potentially use a lot of this same machinery for semiconductor quantum computers. They have fairly low qubit loss rates because you have massive electrons that are confined, and so it's, compared to some other architectures, it's relatively less likely that they escape their jail. Charge qubits are easy to measure, as are spin qubits. Spin qubits are insensitive to electric fields, which gives them larger coherence times, so they last longer. Some disadvantages: maintaining coherence is expensive. These typically need to be kept really cold to reduce noise, thermal noise. And scalability is difficult, although scalability is difficult for pretty much all of the architectures. So someone asked a question related to this. Assessing qubit quality, look for long-lived quantum oscillations. In this type of setup, the way you measure how good your qubit is doing is if you prepare an electron, this is for a spin qubit, in a state, it'll oscillate back and forth between 0 and 1 naturally. That's what they do. They process between the 2 states. And if you prepare a bunch of them the same way and then just measure one at a time, you'll get an average spin value that oscillates back and forth like it's supposed to. But over time, that oscillation will decay. And this is an experimental plot. This is a real plot of measurements that were made. And you can see that that oscillation washes out over time as the environment thermally disrupts the state of these qubits so that they no longer are coherently doing what they're supposed to be doing. They're just kind of randomly doing whatever they want to do. And so to get a scalable qubit, you need over 1,000 oscillations in order to have enough bandwidth to scale this up to a functional computer. Any questions on that before we move on to a different one? How's everybody doing?
Good, excellent.
Yeah? Okay. Great.
I will say you may have given the most technically complex talk we've ever had. I think you're doing a phenomenal job given the difficulty of the material.
Why, thank you.
Excellent, yes.
So another type is a photonic quantum computer. Instead of using electrons as your qubits, this uses photons. And photons then are created from a light source. They travel through waveguides, so just fiber optic cables, pretty basic. You have a bunch of phase shifters, which are just little optical processing devices that can apply electric and or magnetic fields to the photon You can also couple adjacent photons to each other and let them interact with each other. And so you create your photons, you shoot them down these fiber optic cables, and then you do some operations on them and detect them at the end. And then read out whatever your answer is. And there's different ways to encode information in photons. One way to do it is you can have dual rail photons, so you have two fiber optic cables right next to each other, and you move the photon back and forth between the two, and then each, wherever it is, left or right, would be your 1 and your 0. Another way to do it would be have, say, clockwise polarization being your 1 and counterclockwise polarization being your 0, and you can use that as your 1 and your 0 for your qubit operations. And there's some other ways to do it also, but in principle, you make photons, you shoot them down a rail, do stuff to them, detect them at the end, and then read out your answer based on what you measure when you detect them.
I'm sorry, Luke, I'm confused. If you've got a dual rail photonics, the fiber optic cable shielding and casing is, how can the...
We put them close enough to where they can tunnel between the two.
Oh, quantum tunneling.
Yep.
Oh, wow.
Yep. So some advantages of photonic quantum computers are photons are pretty cheap. They're all over the place. There's a whole bunch right in this room. And they're pretty easy to maintain in waveguides. You can operate them at room temperature because photons work pretty well in fiber optic cables. And so they're less sensitive to decoherence in that sense. A caveat to that is that these measurement components often do need to be kept at close to absolute zero to make them work more effectively. But still, it's a big cost saving if you only have to have your fridge on the detectors versus having your entire computer encased in liquid nitrogen. And then also this can repurpose existing linear optic technology, which is pretty well developed. Some disadvantages: photons escape from waveguides at higher rates than electrons or other massive quantum particles. Photons are massless. Just in a real abstract sense, you can understand that something that's heavy isn't going to escape as easily as something that weighs nothing. So photons escape at a higher rate. Also, photons are traveling down these things at the speed of light, and they have to be processed en route, and you can't ask them to hold on for a second so you can do something to them. So you have to sort of carefully construct all this in order to process them as they're moving very fast down these cables, as opposed to with the semiconductor case, you have your electron that's in a dot, you do what you want to it when you want to. So there's some complications that come to making this work, since you have your bits are light that's flying through these cables at very high speeds. Yep.
Can you give examples who's using this, like IBM, Google, what technology?
There's a couple. PsyQuantum is a startup in California that's doing photonic. There's a bunch of other ones too. I'd have to look up what the major ones are. Now I know IBM and IBM is mostly doing superconducting qubits.
And Google is using the same?
I think Google's also. Actually, I have Google and IBM and Baidu are all doing superconducting qubits. There's some of the bigger players. So Amazon outsources theirs. They're doing a cloud-based quantum computing service where they outsource to other companies to make their computers, and you can just query a cloud server that then has these devices, and they do both semiconductor neutral atom qubits, and they have a couple. I think another one that they also do. So I think
So what's all this investment done to academia? I mean, traditionally, you'd say it's at the academics who study physics, but all of a sudden I'm hearing like Google and Baidu and all these.
I think it's overall been good for them, I would imagine. I've been out of the field for a decade, and that was where, when I was doing my postdoc, that's where my grant came from.
Does it gut the professors, where all the good professors leave academia to take industry jobs? Or
Certainly
certainly up all the excess PhDs.
Right. Yeah, no, I think a lot, there is, academia is not doing amazing right now in general, and that's part of why I'm not in academic anymore. It's not as thriving of an environment as it maybe could be. Often really proficient quantum physicists that are good at this stuff can make much more lucrative careers in industry for sure. Third type would be a superconducting quantum computer. This is the same graph we had earlier from that MIT study of a superconducting set of 16 superconducting qubits. So you prepare each of these in a superconducting state. Superconductors are a really fascinating state of matter that is difficult to obtain. But when you get a material to be superconducting, it has zero electrical resistance because the entire object, even though it's sizably large, is all one coherent quantum object. that is able to conduct electricity with no resistance. So as long as it remains superconducting, it can maintain current perpetually without any dissipation of heat. So that has some pretty obvious advantages for quantum computing because you don't have to worry about dissipation in that case. But then you have to keep the entire thing down at a couple Kelvin, which is expensive. And these architectures are, as I said, pursued by Google and IBM and Baidu, among a bunch of other companies. This is IBM's latest offering, the IBM Quantum System 2. It has 333 qubit Heron quantum processors. It is an upgrade from the previous Eagle processor. This is 2 of them, and there's a third one that goes back behind this center post. It is a hybrid classical quantum design. I presume the central pillar is probably the classical part. And one of the major selling points for this is that it's modular. So this has 3 Heron processors, but they advertise that you can just stack on additional boxes to expand this thing out more to get more processing power. And it's sort of built to accommodate a modular Lego growth if you need to expand this device. Yes?
What can you do with it?
Oh, nothing yet.
How much will it set you back?
A lot. I think they do use them for some things. Again, this is getting out of my area of expertise. I believe currently a lot of the use for these is research oriented. Like you can use them for, like as we saw in that study, they were able to show simulating a magnetic field with energy levels. I would imagine that if this thing works as advertised, which I assume it does, then you could use it for research purposes to develop algorithms.
It reminds me a bit of like way old computer days where you had to set up circuits to process a particular.
Oh, sure, absolutely. Yeah, and also I find it hilarious how much this resembles the full room-filled, computer mainframes back from the 70s.
Is each experiment a different result, or are there more general purpose kind of like architectures that can calculate more than one bit?
Sure, that's not general purpose in the way that your CPU on your desktop is general purpose. They're all more customized relative to that. And if you just look back at this one, right? So you have this is a physical picture, right? You have an array of 16 qubits in this arrangement. There's certainly limits on what you're able to do with 16 qubits arranged in a box, right? It's not general purpose.
So Luke, I was going to just address Johnny's question. What you could do with this is you could predict a molecule that does not yet exist interacting with a protein that does exist. You could simulate both of these and try to predict a high binding affinity binding between, say, new molecule X and the serotonin transporter. So trying to make an antidepressant. So that's the kind of thing, predictive quantum chemistry applied to pharmacology. That is a thing people are doing.
It can already do that.
People are doing that research, I'll just say. They're spending a lot of money doing this research. I don't know if anyone's actually made a real new drug yet with this, but it is the kind of thing that they're doing because you do have advantages over classical computing when you're doing predictive quantum chemistry for pharmaceutical design.
So they say is that eventually, theoretically, somewhere in the future, it allows you to sort of multi-thread a calculation a lot faster.
Yep. It'll happen about 15 minutes before Jesus gets back.
But yeah, and to be clear as well, and I mean, Luke can correct me if I'm wrong, but my understanding is to be clear, there are plenty of applications, quantum computers, no matter how many qubits you have, they are not better than classical computers. Like you would not use them. It is not the right tool for that job.
Right.
Aren't they using it for like traveling salesman type of problem?
Traveling salesman? Probably maybe. I'm not sure.
I read it somewhere that okay, don't laugh at me, but UPS is using it for planning routes. Deliveries.
Oh, maybe they are. They are being used currently. I'm not as well versed in what the latest developments are, but yeah, that could be right. Guys, I'm going to try to wrap this up. I'm sorry, I'm going a little over time. Just a couple more slides. Topological quantum computing is a neat one. I won't spend too much time on this. Microsoft did just get a big DARPA grant to try to make one of these. One cool thing about topological quantum computers is that the qubits are not localized states of a quantum particle. Rather, it's a global state of a topological property of a quantum system. So the classical topology example is a cup of coffee and a donut, which have the same topological structure, which means that they're both closed surfaces with a single hole in them. And you can continually morph the coffee cup into the donut without puncturing or breaking any of the surfaces. Analogously, a topological qubit would encode its 1 in something analogous to this donut shape, where even if it gets perturbed by the environment and turned into a coffee cup, it would still encode that logical 1. It's not actually a donut, it's a metaphor, but...
The visual recognition system would go, yeah, there's a bite out of it, it's still a donut.
Right. Yeah, exactly, right. So they're less sensitive to noise for that reason. And Microsoft has a grant to try to make one of these. They say in less than a decade they're going to be capable of 1 million quantum operations per second. We'll see how that pans out. I wish them the best. They're going to use Majorana zero modes to construct their qubits. Those are notoriously difficult to produce, but they did recently publish a paper showing that they were able to make one. You need to make obviously more than one, but it was a good start. And Google and Quantinuum are also working on this type of architecture. Okay, final quick section, just a couple slides. What is the current state of the market? The global quantum computing market was 1.16 billion this year, 2024, and it's projected to grow to 12.62 billion by 2032. So over a factor of 10 increase in 8 years. This is according to Fortune Business Insights research. So pretty sizable market. A lot of people are spending money on this kind of thing. So certainly a lot of people are excited about the prospects for it. This is how it's divided between different industries. Largest chunk is banking, financial services, and insurance. Healthcare, energy, and utilities get a lot too. Automotive, chemical manufacturing, and some other things.
What's driving this market? I mean, if there's no quantum supremacy, why can't I just do all my problems on a normal computer?
Sure. Well, yeah, they're banking that there will be, right? And they want to be the first to get it when they, if it comes through.
Have their staff trained up on something that might someday be.
Right. No, it's all very, it's all very speculative.
I mean, it's very similar to the investment bubble going on with machine learning right now. Much is predicated on assumptions we won't hit diminishing returns. We will see if those bets are correct in the next few years.
Absolutely. This is a little chart that McKinsey and Company made. They did a survey of 300 companies where they sort of gauged what the level of adoption was for companies in different industries. So bystanders are not involved at all. Legends, there's none that qualify yet, but that would be someone that's actually making money with quantum computing. Professionals, this column is mostly the hardware and software companies that are making quantum computers and developing software and algorithms. So this is telecommunications, media, and technology is the main one here, companies that are actually building these things. But then these two, you have sort of beginners kind of tipping their toe into it a little bit, consumer, insurance, travel, transport, logistics, advanced industries, and global energy and materials are looking into it a little bit. Learners are a little bit more invested, automated and assembly, chemicals, pharmaceuticals. Nicole, you mentioned some research that people are doing actively in pharmaceuticals using this type of thing. Aerospace, defense is probably largely cryptography, I would imagine. Financial services. So this is just an overview of what type of industries are invested at what degree in this technology. And then just to looking over the timeline. So back in 2000, there's very little going on. This light blue is volume of private equity venture capital investment. That shot up to $700 million as of 2020. And then a number of quantum computing startups founded was 50 in the most recent year of 2018. So those are both exploding pretty quickly. So there's definitely a lot of hype around it and excitement.
Was there a technical innovation that happened around 2016 that explains it sort of increasing and suddenly starting to go exponential?
Yeah, so this is when I published all my papers.
We'll call it that. For your service.
I'm not sure.
You're not sure. Okay.
It's funny, that is right when I was doing my research.
Well, they say correlation is causation.
Right? I've heard that. So in summary, a lot of hype and potential for quantum computation, but ultimately it's too early to know, so we'll have to wait and see. My personal take, just for what it's worth, I think that they will definitely be useful for something. I think there will be a useful case for them. The scale of that and how far it goes, we'll see. I wouldn't be surprised if it ends up being something that nobody's even anticipating what they're useful for at this point. Like,
Well, I must say we can tell you're trained as a scientist because this is an aggressively non-clickbaity answer.
They're useful for relieving investors of excess capital.
they're very good at that, for sure.
They should be useful for designing quantum computers.
Well, thank you guys for your attention. Sorry for going
More, especially from anybody who didn't speak up yet. I'm sure Luke would love to hear them.
I have a really quick
Yes, sir.
question.
Yeah.
The photogenetic?
The photonic quantum computer?
Yeah.
Mhm.
You said that when it's traveling between the two ends, you can do stuff to photons?
Yep.
How and what would be done to photons? Can you describe that, please? 'Cause I'm
Sure.
not-
You could just have an applied electric field to it.
Okay.
Would be one thing you could do, which or magnetic, which could modify. It depends on how you're encoding your qubits, but you could apply a field to push it from one rail to the other rail, if it was a dual rail qubit, right? So if it being left or right is your 1 and your 0, you move it back and forth to do things.
So applying like magnetic waves to the photons?
Yep.
You do it, okay. I
Yep.
don't know if you like describing something, I don't know.
Oh, no, electromagnetic fields primarily, and then the other thing would be coupling two adjacent photons. So you can have the rails come together at some point, so that the two photons see each other, and they do a little dance. Typically, that would be to get entanglement between the two, so that their wave functions will overlap, and then you'll have entanglement afterwards. So primarily, interactions between photons, and then applying electromagnetic fields to the photons are the primary.
I actually think that might be a good segue because I see some people often kind of like conflating quantum computers with entanglement. Could you maybe clear for the room where they're the same and where they're different?
Well, quantum entanglement is an important aspect of how quantum computers work.
Right.
Quantum entanglement means that there's some coherent relationship between the states of two different quantum particles. So when I had the state back at the beginning, was it here? Basically, it means that these A coefficients are all known and have non-trivial values. It means that there's quantum entanglement. Effectively, it means that instead of the two qubits having their own totally separate quantum systems that are not overlapping and not related to each other, your system is a combination of both of those in some meaningful, non-trivial way.
And due to degrees of freedom in the equation, if you know n-1 values, you know the last value, essentially.
Sure, yeah. Although you don't typically know all these values.
Okay.
At least not in the middle of a computation. But, yeah.
More questions?
Yes, sir.
So I believe that in your day job, you're also working with machine learning and AI patterns and so on.
Yeah, I've done some machine learning also.
So I just ran across the thing that makes sense, which is people sort of attacking quantum mechanics is useless because now we have machine learning based physical simulation, including strong correlation. Maybe you need the quantum computer, but weakly correlated states or something. You can use machine learning and a lot of data to get you the answer really fast enough. That's the new thing. So it's just like one of these wars.
Yeah, I can see that. I'm sure you could see how machine learning could be used to address similar types of problems.
Yeah, once the MIT Technology Forum, which is kind of very popular, what's going on in school, had a call last week or so about that.
It even kind of actually makes me think of, with Owen's example of using a quantum computer for pharmaceuticals, there's been all the buzz about like the AlphaFold algorithm being open sourced, which is also trying to predict protein folding for pharmaceutical application, but using machine learning.
I see. Yep.
Yeah. Is all this quantum computing, like with the pharmaceutical simulation, is that like physically requiring a lot of electricity? Is it very electricity intensive?
Yeah, I'd say so. I mean, the requirements vary with your architecture, but yeah, in general, all of the architectures require tons of infrastructure and super cooled control chambers, and with all the quantum error correction and everything that you have to do to make it operate, you need tons of redundancy. And yeah, these are not simple energy efficient machines for sure. I don't think they're developed enough to where you could really make a comparison, like, you know, sort of a watt per bit. I don't think it's too much in development now to have a definite answer. But there's certainly, yeah, they're not simple low energy devices.
To that end, you alluded a bit to that actually Amazon and AWS will let you rent a quantum computer.
Right.
Do you ultimately see cloud computing becoming the dominant model here precisely because of the immense expense of these machines? Will people rent time like
For consumers, absolutely. Yeah, for normal schmoes like us, yeah.
I mean, do you know what the going rate right now on AWS is? Could normal schmoes like us in this room rent it, or is it still pretty expensive?
You can. I don't know what the rate is.
IBM charges $1.60 per second, so it's for a Heron. So if it was fully utilized, it'd be $50 million a year.
Cool.
I mean, it's in the realm of you could run it for a few minutes, but it gets pricey quickly.
$1.60 a second.
Yeah.
I mean, there have been programs for students, though, to play with these things.
Well, I've heard about them, yeah.
Yeah, there's probably some university devices, I would say.
So Danny Muller presentation about the API to the IBM thing where you could send requests there, but it wasn't very.
Yeah, were you there?
I don't think so.
Daniel ran some Python code on IBM's quantum computer.
Oh, I remember hearing about it.
Yeah, I think it was free for him.
Cool. Yeah.
And that actually, you know, I've heard this, and you, once again, you may know less because you're more on the physics side, but I've heard that because of the nature of that, you can't look at qubits if you don't want to mess everything up. I've heard that most of the programming you have to do on these computers has to be functional programming as opposed to variables. Is that correct in your understanding?
I don't know the answer to that.
Okay.
Sure.
As I said, it might be out of your wheelhouse. That's just
It
what
is
I
a little
heard,
bit.
which
Gotcha.
I thought was fascinating. I mean, it made total sense. Just curious.
Right.
Did I hear about the physical size of these things is huge? So the example you gave with the MIT for the 7-digit, you know, what size computer would that be?
The 16-qubit superconducting one?
Yeah.
Let me see if they have a scale on that. I don't. Yeah, there's a scale. Yeah, we got. This is one. Is that a millimeter? Yeah, that's 1 millimeter here. So pretty small actually. That's about, you know, not that big.
Okay, so it's,
And so just to contrast, so this is real different from some of the other ones where you need thousands of qubits to make a single logical qubit, right? So which is one of the advantages of superconducting, that these are so isolated, and since they have no electrical resistance to introduce dissipation and heat, you can get away with just having a single superconducting object as your qubit. For photonic quantum computing, you need thousands of photons to collectively come together to make your one logical qubit.
I mean, so would it be correct to say if somebody ever cracks room temperature semiconductors, would this be clearly the best way to make a quantum computer?
Superconductors, you mean?
Yeah, sorry, yes.
If we-
Room
yeah, we
temperature
have-
superconductor, I misspoke, sorry.
Yeah, probably so. I think.
Okay, like it would, obviously it's hard to say definitively in every dimension, but this would
Right.
probably be the clear winner if somebody ever cracked
Well, the
that.
fact that they're competitive and the big players, a lot of them are doing this now without their having
It's
room
competitive
temperature.
with still having to get it very near
Right.
absolute zero.
So I would imagine so, yeah. Yes, sir.
Do you know of any good introductory resources that would explain kind of like how these things are programmed or how you put gates together? I mean, from a theoretical level, you explained this very well, but in terms of how you would actually practically put together...
In terms of the algorithms and the gates that you use?
For, say, our prime factorization, how that's...
Sure, yeah. So there's Wikipedia pages on all these things, which would be a place to start. Those are kind of hit or miss in terms of how layman friendly they're written. Sometimes they can be difficult. But there's a whole page on Schro's algorithm. So I'd recommend starting there. I am not an expert on algorithms. I never really studied them. I know, in a hand-wavy sense how they work. There's certainly, tons of books and things written on it.
I will actually say the most accessible thing I've ever found on Schro's algorithm, which when I say accessible, it's like I could barely, after watching the video at a super high level, understand how it worked. I couldn't explain it to you now, but I think actually Minute Physics on YouTube did a 16-minute video on how it works to break the encryption, and it didn't get so into the math that you couldn't at a high level sort of appreciate what it's doing.
That's a great idea. Yeah, YouTube, I'm sure, is a good resource for that. It's amazing how much easier it is to watch a video and understand something.
Yeah, one that has
If it's
nice
well
little
done.
drawings that does analogies just like you did, exactly.
Right, yeah.
There's a group in the UK that, if you will search for a paper called, I think it's called Quantum Computing for Kindergartners. There's a professor that has
method of describing programming and teaches it to kids, and they get it pretty rapidly.
Well, actually, I know there's a company here in town working on quantum computers called Strange Words, that their CEO Worley literally wrote a book called Quantum Computing for Babies. Or not babies, and you can get it on Amazon. I haven't read it yet, but yeah.
I read it and it gave me nothing.
It gave you nothing. Well, if I ever see Worley again, I'll let it know.
Okay, question. How much, what is absolute 0 Kelvin, is it negative 450?
That's negative 273
It's
Celsius.
negative 273.
Negative 273.
It's 400 and something Fahrenheit.
So
yeah.
that's the negative, how much Fahrenheit?
400 something.
400 something, yeah, 450.
Okay, so that's the coldest any object could be in this universe.
Yeah.
So we've got stuff operating just a hair over that. It's almost asymptotically close.
Liquid
to that.
helium is really close.
So I just want to throw that as kind of a mind-blowing thing that, 7 million years ago we had the same common ancestors as chimpanzees. And now we are manipulating objects to be just barely above the coldest anything could be in the universe. So, we live in interesting times, as they say.
And I mean, what that means in practice, coldest really just means that it's literally not moving. It is in a single...
It has no thermal motion.
Right, no thermal
The only motion that it does have is quantum mechanical motion.
Right.
Which is why you have more quantum mechanical effects when it's really cold.
And that's not Browning motion.
Yeah, Brownian motion is thermal, right. Yeah.
In statistical mechanics, the number of microstates, basically, when you have no temperature, you constrain the microstates to where they're just not moving.
Right, yeah, and quantum motion is sort of a metaphor, like but there's quantum energy and dynamics that are changing things. It's not quite the same as rolling a ball
That's
down a hill.
interesting, yeah.
Well, and I mean, temperature gets weird in microstates because actually negative temperatures exist and they're really hot. Like, it's weird.
Right, it does. And in general, like, so if you look at the energy scale of thermal energy at a given temperature and the energy scale of that same system in terms of its quantum mechanical energies, whenever the quantum energy scale gets larger than the thermal energy scale as the temperature drops, that's when you have a dominance of quantum
And you can be
behaviors.
coherent.
And exactly, right.
We're starting to get close on time. If we have any final questions that have not been gotten to, especially who hasn't spoken.
I have a question. Did I understand you right that geckos are walking on walls using some kind of quantum mechanical
Yeah,
effect?
they use the Casimir effect, which is what my PhD research was on. So it's a quantum mechanical stiction force between parallel surfaces that are really close. Their toes have microscopically, very, very, very close ridges on them, and the Casimir effect between adjacent ridges on their toes gives a suction effect that enables them to stick to glass effectively.
Wow.
Yeah, it's neat.
That's amazing.
And it's not suction caused by a pressure difference.
It's not just suction cup. It's
Right.
it's a quantum
To be
mechanical
clear,
effect.
everyone, yeah.
Right. Mhm.
Okay, so that makes me think of something called structured water, which may or may not exist.
I don't know about
Structured water. No, never mind.
I'm not sure.
Fantastic.
Well, thanks everybody. Thank you for your attention.
Classroom so long ago, so thank you very much. Yes, everybody, great. It's been great to have such a robust discussion. We hope we'll see you next month for our holiday party. Stay tuned for news about that. And if anybody needs a voucher for the garage, I have them here. Also, we usually go and get a drink in the lobby and chat, so if you can stick around, we'd love to see you. If not, we'll see you at the next one. Thank you all for supporting what we do and making for robust, interesting discussions. So, later.
Thank you.
Yeah, that was really interesting.
Thank you, John.
Yeah.
Thanks for the invite.
Yeah, we did get that archived.
Great.
Hope it.
Yeah, I have some friends that couldn't make it but wanted me to share the video.
I'm tired too.
Congratulations.
Well, thank you so much. Oh, great. Actually, I gave a general relativities talk to a layman audience years ago. We'll get your contact info. Great.
Talk, man.
So glad you made it.
Yeah. So this is a good question to do where you
Oh, great. I might go sit in the park. I might go see if anyone wants to chat.
Yeah. I'm gonna take off tonight. Yeah, it was cool.
So your slide's gonna be available?
I can make them available.
No,
Yeah, I'll talk to Kevin.
take this week to get it done. Sounds like, it's working, sounds like your schedule's working. And as I said, you get it done, well, sci-fi authors, and I'm sure it's gonna be on things rather than us, probably, so. We may talk to lots of topics.
And setting up there and staying. Are there cosmological?
I think so much, yeah. Yeah, no, it's all good, I'll get that today, and I'll also get it to
Well, typically that is coherent state. Yeah, so, like the sun is a big variable, right? So,
but I'm just, I was just thinking about this, is that maybe, you go to all this effort to do things on a small scale. There's other,
so one context, I'm going to look at it now. So from the sun, you have all spectrum, all
you have assuming that in deep space, you have, nice, cold,
Sure, right. For photonic computers, they used to have a very precise laser generator that makes it through the thing of a single photon. In order to get everything right, in order to be able to control it.
I made this for Caltech.
So yeah, I think it would be difficult.
Yes, they make the garage.
I'm talking about, something that, like radio, are there events cosmologically that you can almost
Just the free screen part.
like piggyback on?
But I'll try to give you
Yeah,
options, especially our
I haven't looked into it, but I would imagine that there would probably be no you would have no way of knowing what's in it.
I understand it, I'm working on thinking of like how to upgrade and get you.
So yeah, it's interesting to think about.
Chris Callan. So, I was in chip design originally, but now I've just been doing, computing and a bunch of crazy things. So,
We've actually done some penetration testing on how long they're valid. But we've had success with some people who translate not I was
sorry, did you say you did have a slide in the middle?
I can think of it. Yeah, I have something. Are you more just
Well, I'm interested in EFF, and I've known them for ages.
I'll try to get them both to share them out once I get it posted. I'll put them on the
Yeah, I was like, all that stuff fuzzy in there. I just read like operators, fermions versus bosons. It's like I don't know what this one, so they're really
Way above some of us still such a good example. Like it's inherently interesting. So even if you're never gonna get close to the math, just the basic subject is knowing that this kind of interest is there, and then seeing how they're trying to make it work.
Right, I'm trying to make it work, right? Yeah.
It's very, very interesting.
Well, you have to remember
For just a generalist, it's really
most of the history of math, people thought there was no point to number theory. It was just mathematicians who used it themselves. And then public key cryptography happened. Yeah, for 2,000 years, people were like,
smart people just drawn to it and turn into something. So it's interesting too that you found yourself sort of migrating from the skeptical side to being more open to maybe there's going to be some useful stuff there. So on the supremacy side, I guess I've seen it in popular press. Also, it's used in a complete different sense. It's like, well, Vandenberg, the Chinese, supremacy first, or maybe some corporate entity versus some other. It's interesting that that's really not what So, I asked you about, is it your impression that if that happened tomorrow, right, we know it?
suddenly everybody's accounts are different or something's changed?
I would say it's certainly likely it does happen. Whoever figures out with this
I'm Johnny. That was very interesting. Did I understand correctly that you said that when you perform, whatever arbitrary calculation, the answer that you get is not actually right answer. You got to do multiple times and perform that calculation multiple times. So you have a
where that probability is as high as you like. You have to run that.
That's pretty good.
You see that twice.
Practical. Yeah. And then you also, there was something on there about text. She said something about how vulnerable
So what that study was showing
today, it's like we're probably all the product of
but over time, you always want to figure it out. So that after a while, so you want to be able to have it
so in order for it to be power to be great enough for it to maintain I don't like the terms.
So basically, we're able to combine it with other qubits and have redundancy the correct quantum error corrections. So putting together multiple ones, you want to be able to do operations on it as a probability of that. You want to do this all before that one.
So it's sort of like a top. You got to spin it out fast.
That's exactly. You want to spin it fast enough to where the top has to be spinning fast enough to where it spins around 1,000 times before it starts to wobble. In order to be able to do useful stuff.
Okay, that makes sense. Yeah. Okay. Alright. You can use that. Just credit the guy. This random dude.
Yeah, they'll make a little video. You can visualize an array of 100 tops all spinning. Yeah. Right? They're all spinning and behaving themselves. Like, oh yeah, I can see how I can do something like that. Then when they start wobbling around.
Right. And then sort of when it starts getting all of this noise happening from the outside, that would be like sort of stable underneath it moving to a degree. And if it's like spinning slow enough that it can't withstand the spinning fast enough that it can't.
Yeah. The reason that even without stable moving, they do wobble eventually. That's just friction. So if you do it on ice,
right. Yeah. Have you seen those? This is totally unrelated. Like gyroscopes on boards tending in waves. It's amazing and instantaneous. It's incredible. Like just look it up on YouTube. Yeah, gyroscopic boat stabilization. It's really yeah.
So you don't get seasick like it's on.
It's like about as flat as you can expect it to be in like choppy waves. Yeah. Thank you very much for doing this. Less introductory than I expected. I'll say that.
I wasn't really sure what level. Like I was.
No, I understand. Until you show up to these kinds of things, you don't know.
Yeah, so we got something like a few more like introductory basic physics slides.
They got it right.
Yeah, right, yeah. Let help figuring out like what to do about
You're not the only one. He's all in the radio. Communication between software.
Okay, are you staying in London? No, pick us up. Good reminder.
Yeah, when we talked at the, we were just
Gotta go.
Test on Thursday. If you wanted to.
So I would say it's kind of like an edge case, and I also just want to back up.
Hey, y'all, they're kicking us out.
Oh, sorry.
But I'll tell you that the guy who's like, he's pretty experienced, but he says like, I couldn't do this by myself. I don't know.
Yeah.
You would have to give me like a 30-page instruction manual or something. I think you're over.
Yes,
it's
over
not
doing it a little bit.
It's not gonna be.
I figured we'd have my laptop up on the podium with Zoom, and doing the webcam as a backup, and my projector as a backup.
I think that's,
You know.
yeah, I can, you could get a really, really minimal version of it where you would just basically have some news thing.